Next theorem or example, let H be a cyclic subgroup of a group G. H is a cyclic subgroup of G and H is normal in G also, that is cyclic normal subgroup of G. Then every subgroup of H is normal in G. Then every subgroup of H is normal in G. Let's prove it. Let us consider some K subgroup of H, which is a subgroup of G. Now it is given H is cyclic and normal. We need to prove K is also normal. Now will K be cyclic? Answer is yes, because we know that subgroup of a cyclic group is always a cyclic group. So when H is a cyclic group, K will also be cyclic. We have this property. We need to prove K is also normal in G. Okay. So for proving that, we are considering some X belongs to capital G and some K belongs to capital K. We need to prove that XK X inverse must belongs to K by the test of normality. Now when H is a cyclic group, H must have some generator. Let's say H is generated by A. Okay, and K is also a cyclic group. Let's say K has the generator some B. Okay, now this B also belongs to H because B belongs to K, this subset of H, and H is generated by A, so that B must be some A to the power M form, right? So H is generated by A and K is generated by A to the power M. Now starting with xk x inverse, put the value. Now K belongs to capital K, which is generated by A to the power M. That means this element will be of the form A to the power M whole to the power some R into x inverse. This is equals x A to the power R whole to the power M. We can change the position of the index. This is equals to this. Now we can write this is x A to the power R x inverse whole to the power M. Now how can we write this? We can check it in rough. X A to the power R x inverse whole to the power M. That is x A to the power R x inverse into x A to the power R x inverse into dot dot up to M times x A to the power R x inverse. Check x inverse x going to cancel out. For the next term also x inverse x going to cancel out, and so on. Ultimately you will be ended at A to the power R A to the power R dot dot A to the power R M times into x inverse. Okay, that is x into A to the power R whole to the power M x inverse. So this is why we can write this line equals to this line. Now this whole quantity must belongs to the set capital H, right? Because H is a normal subgroup of G. We already know that. So xh xk x inverse equals to this whole quantity whole to the power M. Now whenever this thing belongs to H, it will be of the form, say suppose H3 whole to the power M, right? For some H3 equals to x A to the power R x inverse, which clearly belongs to capital H. Now capital H is generated by A. So H3 must be of the form, say A to the power P whole to the power M, that is A to the power M whole to the power P. Now A to the power M is the generator of K. Now it is A to the power M some power, it's some power, that is must belongs to K. Okay, so we started with x belongs to G and K belongs to K. We ended at xk x inverse belongs to K, that is K is normal in G. Okay, this proves the example. Next example is prove that SLNR is a normal subgroup of GLNR. I guess you already know what does it mean by SLNR and GLNR. let me recall it. GLNR means the set of all non-singular n by n matrices over R. And SLNR means the set of all non-singular n by n matrices with date value, that is determinant of A, is equals to 1. Okay, probably we have proved it that SLNR is a subgroup of GLNR. Now we need to prove that it is a normal subgroup. So we will prove by using the test of normality. Let us consider G is our group, that is GLNR, and our subgroup is SLNR. Let's take it as H. Okay, we need to prove we are taking one element A from H and another element B from G. We are considering capital AB because these are matrices. So by the test of normality, what we need to prove? We need to prove that BAB inverse must belongs to H. So what is the property of belonging to H? H means our SLNR. That means the date value of that matrix must be equals to 1. If it satisfies this property, then it will belong to SLNR. So let's start with date of this thing. Applying the determinant property, this means this date B inverse, putting this and this together, now this can be written as date of BB inverse. BB inverse is I into date A, and determinant of identity matrix is 1, so 1 into date A, and date A is already 1 because A belongs to H. This is the property of being an element of H. So 1 into 1, 1. That means BAB inverse belongs to H. So H is normal in G by the test of normality. Okay. Next we have another theorem which is very easy. Intersection of two normal subgroup is normal. I'm leaving it as homework. This is the easiest theorem. Just take two subgroups A and B. We need to prove their intersection will be a normal subgroup if they both are normal. Okay. Moving to another example. Let H is a subgroup of G and A belongs to G. Then this set AH A inverse, which is defined as AH A inverse for some H belongs to capital H, is a subgroup of G. Only subgroup. May be normal, may not be normal. So if H is a subgroup of G, then for some element A belongs to G, AH A inverse, this is defined as this, must be a subgroup of G. Now this is actually an example of the subgroup chapter. We already know from the subgroup chapter that to prove a subset is a subgroup, what are the properties? The property where suppose H is a subset of a group G, then to prove H is a subgroup, we need to check two things. Number one, A composition B belongs to H for all A comma B belongs to H, and A inverse belongs to H for all A belongs to H. If these two conditions satisfied, then H is a subgroup of G. So we need to prove the same thing for AH A inverse. Okay, so let's take two elements. Let P comma Q belongs to AH A inverse. Then P will look like some AH1 A inverse and Q will look like some AH2 A inverse. Okay, so P composition Q will be opening the bracket, A inverse A will give you E. So A, H1, H2, A inverse. Now H1, H2 must belongs to capital H because it's a subgroup. So this whole thing belongs to AH A inverse. Okay. So So P composition Q belongs to AHA inverse. Similarly, we need to prove P inverse also belongs to AHA inverse. So starting with P inverse is AH1 A inverse its whole inverse. According to the formula, it will be A inverse its inverse, H1 inverse, A inverse. A inverse its inverse is A, so A H1 A inverse. Now when H1 belongs to H, H1 inverse also belongs to H because H is a subgroup. So this whole thing belongs to AH, A inverse. Okay. So we starting with P and Q belongs to AH, A inverse, and we ended at their composition belongs to the same set, and its inverse also belongs to the same set. That means it's a subgroup. Okay. Now this subgroup has a particular name which is called conjugate of H. This subgroup has a particular name which is called conjugate of H. Now it has something related to normal subgroup. We need to prove that. So our next theorem is a subgroup H of G of a group G is normal if and only if AH A inverse equals to H for all A belongs to G. Okay, if and only if AH A inverse equals to H for all A belongs to G. That means H is a self-conjugate subgroup. So the statement might come in another way, that is, prove that a subgroup H of a group G is normal if and only if it is a self-conjugate subgroup. Okay, the same thing. Self-conjugate means AH A inverse equals to H. That is conjugate subgroup and the subgroup itself are same. So prove it. Proof is very easy. Let's take H is normal in G. Proof. Then H equals to HA for all A belongs to G. Starting with some P belongs to AH, A inverse. So P must be look like some AH1, A inverse. Okay, we can write it, this is equals H to A inverse. Okay, because H and H to A are same because H is normal in G. Then A inverse and A will give you E, so H to E, this is equals H2 belongs to H. Okay, so AH A inverse is a subset of H. Similarly, we need to prove H is a subset of AH A inverse, that is H equals to AH A inverse. That means H is a self-conjugate subgroup. This goes to the necessary part. Now similarly you can prove the sufficient part also. I am leaving it as homework. This is quite easy. Okay.